I want to do 3 examples to try to show you these techniques. And I'll start off fairly simple, and then by the end, I want to be more complicated. So I want to take this result here, and I want to apply it to these examples here. So I have 3 examples that I want to get through. So, and I'm not going to finish them all today, by the way. I won't do them until I'll finish this up on Thursday. Okay, so let's go do the first example. So the first example reads this here. So what I want you to do here is that when we read it, we want to define a coordinate system. In this case, it's got to be right the north, east, southwest coordinate system. I want to be able to draw a vector picture using the parallelogram rule. And then I want to do a mathematical calculation or representation of how to get the final magnitude and direction of our vector here. So here we go. A person walks in the following pattern. So immediately when I'm thinking pattern, I'm immediately in my head going like, I need a coordinate system. So what coordinate system am I going to use? North, east, south, west. Okay. So it says here that we're going to move what 3.1 kilometers north, then 2.4 kilometers west, and then finally 5.2 kilometers south. So there's 2 ways of adding vectors. So the first one is the physical picture, but the physical picture is not very good at doing calculations. We want to do the mathematical one to actually get the final resultant. So let's do the physical picture. So the first one here is the physical picture. And this is the picture that if you were walking this is exactly what you would do. So the first thing that I'm going to do here, of course, is that I got to set up a coordinate system. So let's go do this. So here's my coordinate system. And let's say that it looks like this here. So the longest length is 5. So let's see how this turns out. So I'm going to say that 1 square. So I'm going to say that 1 square in my OneNote is 1 kilometer. Okay. So let's go do that. So I'm going to walk 3.1 kilometers north. So note again, this is north, right? And this direction, this is west. And then of course, this is south. So my first vector is A, and I'm going to say that it walks 3 squares. Is it 3.1? Yeah, it's a little bit more than that. But I'm going to, since this is a rough picture, I'm going to say that this is my picture right there. And this is my vector A. And this says that it's 3.1 kilometers north. So note that I have 2 pieces. Now it says that I'm walking what? 2.4 kilometers west. So I'm going to go essentially to this middle point. So then here is my B. And then this B here, I'm walking 2.4 kilometers. In which direction? West. And then finally here, I'm going to walk 5.2 kilometers south. So if I do that, that means this is 1, 2, 3, 4, 5. It's going to look something like this. So then in this case here, this is going to be C, and this is 5.2 kilometers, but this guy's moving south here. So what I'm seeing here is that there's a resultant vector. In other words, I have a vector that looks like this. So I'm going to call that vector D, and I'm going to say in this case here that D is the result of A plus B plus C. And right away, what you're seeing here is that, of course, everything is measured relative to the origin. So if I had to walk like a bird flies to get, to this point here, I would fly along the point D here. But it turns out that even though this is the physical picture, it's not the most useful picture. So this one over here, this is the best mathematical picture. And what you do here is that you take all vectors and you put their tails at the origin. So this tells us here is to take all vectors and place their tails at the origin. So let's say that this is the origin right here. So I'm going to take my red. You can see that the red is already that way. So here I go. I'm going to go 3 kilometers up. Look at the green. I take that green and I want to put it right here. Then I take my blue and then I'm going to go straight down because it goes south. So I got to go 5 squares.
Hey, Carlos.
Yeah.
I see that you give us our formulas up at the top of this handout. Is that something we will be given on a quiz and exams?
Well, since this is open book, you have access to them all the time.
Oh, right. Okay. Thanks.
And you know what? You should, my memory is like really bad. So the thing that you really want to do here is that I actually have an equation sheet that has all of the equations for the first exam. And that would be really, really useful to you. And if enough people remind me in my old age here, I'll remember and go like, oh yeah, this would be useful to you. So if you could help me out, that would be really great.
Okay.
Okay. And most students really like that. But let's do the parallelogram rule now, right? Let's do the parallelogram rule. So here I go. Check this out. If I do the parallelogram rule, what am I going to get? I'm going to get something like this here. So that means I have a vector that does what? Like this. That's A plus B. So let's do that then. If I look at A plus B, so this guy's then going to look something like about right here. Let's see. So that's going to look 1, 2, 3 squares. It's going to be about right here. So if I now do the projection, and I now do this guy here, what you're going to see here is that, look what I get. Remember, this is hand drawn, so it's not like, look how I get the exact same vector. And you got to admit, this is much easier and cleaner. You do not want to do the physical picture. It's the worst picture that you can get. So what do we want to get to? We want our magnitude, right? So we want the length of D. And the other thing is we want the angle here. So how do we measure that angle? Most angles are measured relative to what? The x-axis. So when we think about the angle, we typically think about the angle all the way from here to here. And you're going to see here is that in most physics and engineering classes, we actually don't want the angle from the x-axis. We want the angle from the negative x-axis, not the positive x-axis. But let's go and start this calculation so that you can see where I'm coming from. Okay, so if I look at this thing, what do we want here? We want our results. Okay, so picture-wise, We want the magnitude. So let's be more detailed now. So detailed means I want the magnitude of D, which I write like this. And remember, you sum and square all of the X and Y components. But note, there's 3 vectors here. So it should be what? AX, BX, CX squared. And then I do the same thing with the Y's. And then I take the square root. That's what we expect. And if I want the direction, then I come in and I say, I want the angle. And of course, it's what? It's all of the Y components. So in other words, this is AY, BY, CY divided by AX, BX, CX. So we want to calculate the angle of D and this magnitude of D exactly this way. So let's go look at these guys. So my whole goal is to get components. So let's go do that here. So let's start off with the first vector. So I'm going to start off with vector 1. So not vector 1, vector A. So when I look at that vector, look what actually happens here. So when I look at the components of this vector, we see here is that this vector is only in which direction? The Y direction. You could see here that the AX term, that there's nothing in the X, it's all in the Y. So I can immediately come over and say what? That the length of this guy is then going to be 3.1 kilometers, because that's what it told us. But wait a minute, what does this tells us here? So if I look at this guy here, look what this tells us here. So the physical way to look at this thing here is we say, okay, I have this vector A, and I clearly have this, and I see that that must be exactly like this, right? And so we could do it this way here. And so what this tells us here is that the magnitude of A is all about AY. Okay, so let's go to the next one here. So if I look at vector B, what we see here is that that vector is along where? It's along the west axis. In other words, it's going in this direction here. And you could see that in most coordinate systems, we define positive and negatives. Since that's the customary way here. And you could see that in this case, this AX here is then going to be given by what? 2.4 kilometers. But note that AY in this case is 0. There's nothing pointed in the west direction. Excuse me, in the north direction. So when I've been calling this A, I should have been calling this B. Let me erase this. So this should be B. So then I could come over here to my B vector, and I could call this BX, BY. And of course, when I look at this by hand, I'm putting in, well, yeah, the negative sign is telling me that it's in the west direction, and that has nothing here. So when I go and I look at the magnitude of B, the magnitude of B in this case has to be what? Has to be exactly BX, which is of course 2.4 kilometers. And over here, it should have been 3.1 kilometers. That's the length of the vector. The plus and the negative sign gives us the direction here. And then if I finally go to the C vector, and this scenario here, we see that it's pointing in the negative direction and the south direction. So if I look at this guy, we see here that C is in the Y direction, and it has a length of what? It has a length of 5.1 2 kilometers. And of course, CX is of course 0 because there's nothing along the x-axis. So when I write this vector, what we're really saying here is that this is CX, CY. So of course this is 0. So by hand, I come in and I do what? I put in the negative sign because it's in the south direction. And then I put the magnitude in this guy. So when I look at the magnitude of C, of course, it's the same as the magnitude of CY, which is a positive 52 kilometers, because that tells us exactly what the length is here. So now when I go and I start to sum the vectors using our vector addition thing, here I go. I said that D, the magnitude of D, was going to be what? It's going to be AX, BX, CX squared. You know what? I'm going to do this differently because I think it's going to, I'd rather be a little bit more systematic. So the vector D looks like what? Well, D has components of A, B, C, which means that this is AX plus BX plus CX. And I can write that as a point, AY, BY, CY. But wait a minute, we can simplify this thing. Why can we simplify this thing? Because remember, when I look at X is 0, so I could come over here and I could go, but wait a minute, that's 0. And when I look at C, you could see that C here, CX, is also 0. And then when I look at the Y components, you could see here that BY is 0, but not the others. So then I can do this. So it really simplifies it to rewrite this as what? BX and then AY plus CY. So that's really the vector that we're dealing with. So when I look at this thing, I'm going to add these values. So what do I know? Well, I know that BX is what? It's negative. So I'm then going to write minus 2.4 kilometers. I'll put the units out afterwards. And then AY is what? 3.1 in the positive direction, but CY is negative, so I'm going to write minus 5.2. And this is all in units of kilometers. So now that I have that, I could then find out what my vector looks like. My vector looks like what? It looks like it's going to be 2.4, and then this has to be a negative number, which is minus 2.1 kilometers, and that's what my vector D is here. Now the question is this vector realistic? And what we have to do here is that we have to go back to our parallelogram rule. So let me go get that image and bring it down. So here I go. So I'm going to come up and I'm going to grab this picture right here. And when I come here, what you're seeing here is that, look at the picture now. Look at where D is pointing. D is in what? It's in the third quadrant. And the third quadrant says I should have 2 negative components. And what you're seeing here is that I see 2 negative components. So that's looking good. So now that I know that I'm at least in the right directions mathematically, I want to go in and I want to calculate the magnitude and the direction of this vector. So let's go do that now. So here I go. So I have my vector. So here we go. So now we want to calculate the magnitude slash direction of D. So here we go. So the magnitude of D, as we've already talked about, is going to be this guy right here. So this guy has what? It has dx squared, dy squared, square root. So what's dx? It's going to be minus 2.4 squared plus negative 2.1 squared square root kilometers. So if you compute that, I get a value of, for D, I get 3.2 kilometers. So I now know the magnitude, the length of that purple vector. Now let's go calculate the angle. If I go calculate the angle of D then is the tangent inverse of dy over dx. So if I put those in, I'm going to get the tangent inverse. And the thing that you're seeing here is that, look what I'm going to get. I'm going to get the y component, which is 2.1, divided by the x component, which is negative 2.4. And the thing that's really important here is that look at this minus signs. They cancel out. So when you calculate this thing, you get 41 degrees. So the question is this realistic? Well, what does the angle 41 degrees mean? Now remember, everything that we measure is relative to the positive x-axis here. Okay, so let's go look at this thing here. So all angles are measured relative to positive x-axis. So when I look at this picture here, what does this tell me here? It's telling me that the angle of our D vector is pointing in this direction at that angle here. But you can see that that can't be true because this angle's in the first quadrant, this angle's in the third quadrant. It's not right. So the question is, we want to ask the following question. What does this angle 41 mean? And if we're going to measure something relative to the positive x-axis, how do I get to that?
Isn't it in the negative direction? So you go the clockwise from the x-axis will get you 41 degrees.
Yes, you're right. And according to what they're telling us here is that we have to do something. So we were looking at this example, and when we were looking at this example, one of the things that we said here is that there's a physical picture and then there's a mathematical picture. The physical picture, you literally just follow the vectors, one at a time as you go along. The mathematical picture, which is what I strongly encourage, is that you literally take all vectors and place their tails at the origin. And what I was showing you here is that you could see that the vector D is the same in both of these pictures here. So then we went in and we says, we're going to look for the vector D, which is the sum of A, B, and C. And so when we go get the magnitude, we sum their x's and square them, sum their y's and square them. And then when we get the direction, we take the tangent inverse of the y's divided by the x's. So what we did here is that without any angles, what we focus on is we focus on the components. In other words, when we looked at the vector A, the x component was 0, so we only focused on the y. When we looked at the vector B, we only focused on the x and not the y. And the same thing with C. So by looking at if you have vectors along the axes, then we can immediately come in here and say, okay, these terms must be 0. The whole point of that is that it simplifies the picture. That's the important piece here. And so once we simplify the picture, what we're actually seeing then is that we get a value for D. And you can see that we have two negative values, implying that we're in the third quadrant, which is exactly what we expected from our initial using the parallelogram rule to add all of these vectors. So now that we have the vector D, we then want to go in and calculate its magnitude and its direction. So that's what we did. We calculated its magnitude, and we found that it had a length of 3.2 kilometers. And then we calculated its direction. And the thing that you should be paying attention when you're looking at the direction, note that there are signs here. And these signs right here, they cancel. And they give you an angle of 41 degrees. So when you're doing these calculations, one of the things that you want to pay attention to here is that you want to focus and say, look at the sign cancellation. And so when you're looking at the sign cancellation here, what this is really telling you is that the answer will be in the first quadrant. But the problem is, we know that the vector's in the third quadrant. And so when you go to calculate the angles, you want to see how those signs are set up. Is it minus minus? Is it minus divided by a plus? Or is it a plus divided by a minus? Or is it a plus and a plus? That's where you got to really pay attention. And your spider senses should be going off, because you know that something's awry here. So what we want to do then is that we want to come in and we want to look. So what was the mathematical calculation here? So now what we want to do here is that we want to look at the angle carefully. So if I set up my coordinate system, what am I actually seeing here? Well, the problem says that we have an angle of positive 41 degrees, right? So this is what the math is telling us this. But we know it's in the third quadrant. So what we want to do here is that then when we look at the vector D, we know that it's actually in this quadrant. So the way we connect these two here is that we have to add what? We have to add 180 degrees. So if you're looking at the standard math answer, what they say here is that the angle of D is then 180 degrees plus the 41 degrees, and that this angle here is then going to be 221 degrees for the angle D here. And you have to be careful. You have to state where all angles are measured from. So this is measured from the positive x-axis. Now, the physics answer / engineering answer is not to do that at all. In fact, if you look at this picture here, if this angle is 41, this angle is 41. So if you give me an answer of 221 degrees and you say it's measured from the positive x-axis, then I'm saying, okay, good, no problem. But you're going to see transferring that angle all the time can get very cumbersome and misleading. So what we say here is that we know that if we have this vector D and I calculate that 41 degrees, what you want to do here is that remember, right? So when I say remember, that we knew the angle was always in the third quadrant. So if you came in here and just said, that angle right there is my 41 degrees, and then you say, we measure this, I'm running out of space, so I got to move it over here. So then if I come over here and then we say, we measure 41 degrees from the negative x-axis, then I'm going to say, good job. Both answers are good, but which do we prefer in the sciences and engineering? We prefer the latter one. That's what we want.